Here. All right, we should be set. Can you hear, is there any less background noise from the air handling system than there was?
Yeah, a little less.
A little less, okay. So what I did was I turned on a noise suppression instead of a noise reduction. That's great for reducing background sound, but I'm not sure, when I walk further away from the mic, it might think I'm background noise and suppress me as well. So you'll have to let me know if that's the case, and I'll go back to the original settings. So I could actually try to wear a mic, but my wireless mic doesn't work very well, so it's kind of a problem. So can you still hear me from over here?
Yeah, it just sounds like you're far away this time.
Okay, so is it better or worse?
Oh, now I can't hear you.
All right, so I changed the settings back. I was afraid that when I moved too far, it's really designed for like podcasting and thing. I was afraid when I moved to the board, it would treat me as background. So we'll have to live with the previous one. Hopefully it won't cut out so much. So we talked about three methods for converting three different functional groups to carbonyl compounds. We can convert alcohols by oxidation with chromium 6 reagents. We can convert alkenes by oxidative cleavage with ozone. We can convert alkynes by either antimicrobial hydration with a boron reagent followed by aqueous basic hydrogen peroxide, or Markovnikov addition using mercury catalyzed hydration with aqueous acid. There are other methods, and one of them that's very useful for aromatic compounds so taking an aromatic compound and converting it to a ketone or an aldehyde so using benzene, you can acetylate it and make acetylbenzene. Or we can make benzaldehyde. And both of these are named reactions. Organic chemists love to have named reactions. To make the ketone, it's the Friedel-Crafts reaction. And it's Friedel-Crafts acylation. That acyl group is this carbon-oxygen double bond connected to another carbon. And to make the aldehyde, it's the Gattermann-Pulp reaction. And these are closely related, but the reagents are slightly different. So to convert benzene to acetylbenzene, the reagents are acetyl chloride and AlCl3, and that's often run in a somewhat polar solvent like nitromethane, because nitromethane is polar enough to dissolve the aluminum chloride, which is a salt, but also non-polar enough that it will still dissolve the aromatic compound. So that's the Friedel-Crafts acylation. The Gattermann-Pulp reaction involves two of the same reagents, the acetyl chloride and the aluminum chloride. Sorry, the aluminum chloride, right, it's the same reagent. But because formyl chloride is unstable, and you can't actually buy formyl chloride, we have to make that in place by adding HCl and carbon monoxide gas. And then there's another catalyst in there, copper 1 chloride or cuprous chloride. we're making the formyl chloride in situ from those two gases. The gases don't react very readily with each other, so the purpose of the Cooper's chloride is to complex with the triple bond. Copper 1 likes to complex with triple bonds, and we saw that in the palladium catalyzed cross-coupling, the Sonoga-Shira reaction last semester, where we had an alkyne coupling to an aromatic compound using palladium 0 and a copper 1 reagent. So it's the same principle. The copper 1 binds to the carbon monoxide and makes the carbon monoxide more reactive. So we can talk about the mechanism of this reaction. We have aluminum chloride, which is electron deficient, right, with aluminum having an unfilled octet. And we have a reagent that has atoms with lone pairs. So the chlorine of the acetyl chloride can actually bind to the aluminum. Taking aluminum tetrahedral and putting a positive formal charge on that chlorine that's bridging between the carbon and the aluminum. That's not that stable, and tetrachloroaluminate is. So that can now spontaneously fall off, form the tetrachloroaluminate ion. Stable complex ion, and the acylium ion. And the acylium ion is stabilized by resonance. Because we have a lone pair on that oxygen, you can write a resonance structure that has field octets and the positive charge on the oxygen. And so we'll usually show it as the better of the two resonance structures, which is the one on the top. But reactivity-wise, it's often the minor resonance form that tells you the reactivity. And what that tells you is this carbon is really electron deficient. That's a very electrophilic carbon. So the pi bond of the benzene ring, which is relatively unreactive, it's not going to react with just any electrophile. It makes a really strong electrophile. Because when this pi bond reacts, that is going to break the aromaticity of the benzene ring. And there's about a 30 kilocalorie per mole resonance stabilization or aromatic stabilization energy. That comes from the fact that we have those three double bonds together in a six-membered ring. Has my voice cut out at all this time? Have I been stable?
You're good.
Been stable?
I think it's better.
Okay, good. So maybe some of the settings. I changed some other settings too, maybe it helped. So this has broken the aromaticity, so this is not very stable. And what will happen is this hydrogen will then be plucked off by the tetrachloroaluminate ion. One of those chlorides will come off. And grab that hydrogen and return that pair of electrons to the aromatic ring. giving the product, plus HCl. And regenerating the aluminum chloride. The aluminum chloride then ends up binding to the oxygen. So you need a full equivalent of the aluminum chloride. It's not catalytic because the product oxygen will bind to fill that octet on aluminum, and you will get, as your product, this complex. I'm not going to show them, I'll just rub them out as Cl3. And that'll stay that way until you work that up with sodium bicarbonate or something, which will then neutralize the HCl and take that aluminum chloride back off. So it's a full equivalent of aluminum chloride and acetyl chloride and sometimes dichloromethane, but nitromethane is a really good solvent for this reaction because of its increased polarity. This is a polar aprotic solvent, right? Much more polar than CH2CO2. So that's the Friedel process. This mechanism, this two-step mechanism here, where we have electrophilic attack in the first step, of the aromatic ring onto the electrophilic acetyl group, followed by a proton removal. That is the electrophilic aromatic substitution mechanism. And that electrophilic aromatic substitution is the only one of the 6 major mechanistic classes of reaction that we didn't talk about last semester because we didn't deal with aromatic systems. We introduced nucleophilic alkyl substitution, nucleophilic acyl substitution, nucleophilic acyl addition reactions with Grignards and hydride reducing agents, and then we did electrophilic addition to alkenes, but we did not do examples of electrophilic aromatic substitution. It's simple. It's a two-step mechanism, right? The benzene ring or the aromatic ring attacks your electrophile, and then something comes in and removes that proton. The catch is it needs to be a very strong electrophile. So the kinds of electrophiles that will react with ordinary CC double bonds of alkenes or CC triple bonds of alkynes won't react with benzene rings. So we've got these 2 additional steps here designed to take the moderately electrophilic acetyl chloride and convert it into the hugely electrophilic acylium ion. Okay? And that's just the chlorine attacking the aluminum and then the tetrachloroaluminate ion falling off. So we'll see a lot more examples of this electrophilic aromatic substitution in chapters 15 and 16. But this one's important for generating carbonyl compounds from aromatic compounds.
Dr. Lever, before you start erasing a whole lot, I have a question.
Yeah, go ahead.
It's probably dumb, but why
I like those
in
questions.
that
They're my favorite.
I get the removal of the hydrogen to remove the proton, but why does the oxygen want to bond to the aluminum and not get rid of the other hydrogen?
Not get rid of which hydrogen? This one?
Yeah.
If you were to get rid of that hydrogen, you would convert this into an sp hybridized atom. Sp hybridized atoms are supposedly linear, 180-degree angle, but this is constrained to 120 degrees by being in a 6-membered ring. It is possible to put a triple bond in a benzene. It's called a benzyne intermediate, but it's ridiculously unstable. And so it requires really forcing conditions. Right? So your question might be, why can't it do it again? Well, why can't this then react with another molecule? Because we got 5 more hydrogens on there.
Uh-huh.
And the answer to that is because this is electron withdrawing, you've got the electronegative oxygen on there, so that pulls electron density out of the ring. This aromatic ring is actually much less nucleophilic than the benzene ring was to begin with, and is no longer a good enough nucleophile to react even with the acylium ion. Even though that acylium ion is very electrophilic, it's not electrophilic enough to react with what we call a deactivated benzene ring where there's an electron withdrawing substituent on it. That's jumping into chapter 16, but that's why we don't have to worry about double addition. Does that answer?
Okay,
That cover
that
it?
makes sense. Thank you.
The reason why this oxygen binds to the aluminum, of course, is because aluminum has an unfilled octet. It's going to bind to something. And if there's not enough acetyl chloride left, it's going to react with the only lone pair it can find, which is the oxygen of the product. So if you're making a note card for this to study, so you can get this reaction down, what you want to write is benzene, and I'm showing the hydrogens just because that's where the reaction's occurring, and then the product this is the acetylbenzene, and then on the back side, you want to write above your arrow CH3COCl, AlCl3, and nitromethane. Those are the reagents that will accomplish that transformation. It doesn't have to be CH3. Any other R group will work there, and you can have things attached to the benzene ring that are not deactivating. So like if there was a methoxy group on here, this would still work. So sometimes that's shown by just putting an R1 and an arrow that points to the ring saying it could be on any position anywhere else in the ring. So that's your note card version of the Friedel-Crafts mechanism or reaction with that mechanism. The Gatterman-Pulp reaction is very similar. Basically, you have carbon monoxide, right, which already has bad formal charge separation. It's got the positive formal charge on the more electronegative oxygen. You have HCl. The aluminum chloride is going to bind to the HCl the same way it bound to the acetyl chloride, right? Because it wants to fill the octet. So what you're going to make is a stupendously strong acid. HCl was already a strong acid. You can imagine how ridiculously strong it is when it's bound to aluminum, so we have a partial positive, so we have a positive formal charge on that chlorine. That is such a strong acid that it can even protonate carbon monoxide. And the copper copper ion, is bound to that carbon monoxide by what's called a pi complex. So we have that triple bond kind of complexed to the copper, and this carbon can then attack that hydrogen, moving out the tetrachloroaluminate and generate HCO minus or plus. Right? So we get HCO plus, kind of bound to the copper still. And then that electrophile reacts with benzene ring the same way that the acetyl, the acetylene ion did. So once you generate that HCO plus in situ by attacking the aluminum with the HCl and then taking that proton off with carbon monoxide gas, the mechanism is identical for the Gatterman-Pulp reaction. The copper is necessary, though, to render the carbon monoxide reactive enough to actually be protonated, and the aluminum chloride does the same thing. It generates an even stronger electrophile than would be present before. So the Gatterman-Pulp reaction is similar, not quite the same, because of the instability of that formyl chloride. Formyl chloride, if you make it, would just spontaneously break down into carbon monoxide and HCl gas. So you can't keep that. So those are ways ways to convert aromatic compounds to aldehydes and ketones.
That last step you're about to erase, would that be a benzene ring, or was that just
It can be any aromatic ring. I had it as a benzene ring.
Okay, there was only one double bond. I was confused.
Did I not draw all the double bonds?
I think you just drew one, and I was like, I thought this was only for one thing, but then I was confused,
No,
so.
it's an aromatic ring. I thought I had drawn all three. I only drew the hydrogens in one place because the hydrogens are, this is where the reactions occurred. So it's possible I left out the other two double bonds. Mechanistically, it looks the same. We have the attack of the aromatic ring on the electrophile. And that's a very strong electrophile. I'm not showing the copper complex, but the copper is still there, complex to the triple bond, making that more electrophilic. And then the chlorine of tetrachloroaluminate comes and yanks that hydrogen off to form HCl. And generate a double hide. So it's a proton transfer step, just like the Friedel-Crafts mechanism. The only difference.
Where does the copper go?
The copper just stays complex to, it's catalytic in that copper one, so the copper just stays complex to carbon monoxide.
Like, we're not necessarily worried about that. Like, writing out the mechanism, I mean.
No, you don't really need it. I mean, it's there throughout. It's kind of sitting there, forming this pi complex. But when you're writing the mechanism, that's just kind of understood. You don't really need to show it. If you don't put the copper chloride in there, the reaction doesn't work. It's necessary to activate the carbon monoxide.
So it's more catalytic than it is actually reacting.
Yes. It's forming the pi complex with the carbon monoxide, and it's still there, pi complex to this HCO plus ion. But then once you form this, it kind of falls back off, and it's free to activate another carbon monoxide.
Oh, okay, I understand. Thank you.
Unlike the aluminum chloride, right? The aluminum chloride isn't catalytic because the aluminum chloride is going to attach itself to this oxygen. But since the aluminum chloride is attaching itself to this oxygen, the copper doesn't. So the copper is available. There are other reactions that are catalytic with the aluminum chloride, but the Friedel-Crafts acylation is not one of them. Other questions about the electrophilic aromatic substitution? Right? We've got the Friedel-Crafts and the Gadamer-Koch reaction. It doesn't really matter that much if you know them as the Friedel-Crafts and the Gadamer-Koch reaction, but everything's named after someone, usually Germans. Okay, so then, what am I on number 5 here? We have some special oxidations of allylic and benzylic and propargylic positions. So we have to know what these mean. And the allylic position is adjacent to a carbon-carbon double bond. So this would be an allylic alcohol. A benzylic position is adjacent to an aromatic ring. This is the benzylic position. a propargylic is adjacent to a triple bond. So in all cases, what you're talking about is you're talking about a position near a carbon-carbon pi bond. And it's just different. It's allylic if it's near just an alkene, and if it's benzylic if it's next to an aromatic, and it's propargylic if it's next to an alkyne. Being adjacent to a pi bond like that renders you more easily oxidized. Right? So we don't need a chromium-6 reagent. We can get away with a less reactive manganese-4 reagent. So we've got manganese-4 oxide or manganese dioxide, activated manganese dioxide. You'll see that manganese-4 is a less readily reduced compound than chromium-6. Right? It's not permanganate, which is manganese-7, which is a very strong oxidizing agent, so it's a milder oxidizing agent. It's not very soluble in organic compounds, so it's usually used as just a solid suspension, and you stir it vigorously so you get good surface area contact. And it will oxidize the allylic alcohol up to the corresponding carbonyl. So this is a primary allylic system. And it'll generate an aldehyde. But it would do the same for a secondary allylic or propargylic position. So it will also oxidize benzylic alcohols. So if I had one phenylethanol, for example, I could treat that with activated manganese dioxide to generate acetophenone, which is the same thing we just made by the Friedel-Crafts reaction. Right? So in this case, a secondary alcohol goes to a ketone. In this case, a primary alcohol goes to an aldehyde. Those reagents will not react, or the manganese dioxide will not react with ordinary alcohols. So you can oxidize, for example, a benzylic alcohol in the presence of a regular alcohol. So I've got a primary alcohol on this end, but I've also got a primary benzylic alcohol. And if I react that with manganese dioxide, I can convert the allylic alcohol into the aldehyde, the benzylic alcohol into the aldehyde without touching the regular primary alcohol. That's useful, right? To have a way of selectively oxidizing the more reactive alcohol without reacting with the less reactive alcohol. Same thing for propargylic. I haven't shown it, but manganese dioxide will oxidize that up to the aldehyde as well. The benzene ring is even more reactive. If you have an alkyl benzene, so in this case, 1-butylbenzene, or N-butylbenzene, it's possible to oxidize that hydrocarbon, that benzylic position, using a chromium-6 reagent. So treating that with chromium-6 oxide or chromium trioxide. Actually has three names. It's chromium-6 oxide, chromium trioxide, reflecting the fact that it's actually a covalently bonded compound, chromium in the +6 oxidation state. This is normally the way we name molecular compounds, as opposed to naming ionic compounds. So this isn't really ionic. And it's also referred to as chromic anhydride. And that name comes from the fact that it's derived from chromic acid by removal of water. So if I remove the elements of water from chromic acid, I get chromic anhydride, right? Anhydride means without water, chromic acid removing water. So if you see chromium 6 oxide, chromium trioxide, and chromic anhydride, they all refer to the same thing. And they will oxidize a CH2 group up to a carbonyl compound, which is really kind of weird. I'm not even going to attempt to show the mechanism for that because I don't know it. But it takes away these two hydrogens from the same carbon, as opposed to taking away one hydrogen from the alcohol and one hydrogen from the carbon. So it's a way of converting an alkyl benzene into an acyl benzene. And there are reagents that will allow you to go the other way, from this acyl benzene all the way to the alkyl benzene, which we'll talk about later. So the benzylic position can be oxidized with chromic anhydride, and allylic alcohols, benzylic alcohols, and proporgylic alcohols can be oxidized up to the corresponding carbonyl compound using a milder oxidizing agent. And we won't talk about the mechanism for that either. If you were to treat this with a really strong oxidizing agent like KMNO4, it actually chews that entire alkyl group off. And converts alkyl benzene all the way up to the benzoic acid derivative. Right. So that's unique, right? The benzylic position is much more easily oxidized than a regular, ordinary, non-benzylic position. And that's because the transition state has contributions from the pi system. The pi system will donate in and stabilize that transition state. So those are the new reactions that we didn't talk about last semester that you need to know about for this semester. Are there questions on any of that? And these, you just have to know the reaction, right? I haven't shown the mechanisms.
Do those fall in a certain class of reactions, or like would we just, I don't know, like organize it as oxidation?
They're oxidation reactions. They're not really nucleophilic alkyl or acyl substitution reactions. They're kind of...
Okay, that's what I was wondering. Thank you.
Especially this one. This one doesn't fall into any class of reaction. The oxidation of an allylic alcohol, benzylic alcohol, or proporgylic alcohol using manganese dioxide, that does form a manganate ester, and then we would E2 elimination, much like the chromate ester. So if you want, you can kind of put that in the E2 elimination category. And the formation of the manganate ester, much like the formation of the chromate ester, is a nucleophilic acyl addition. So I think I went over the mechanism for the formation of the chromate ester last semester, and said, don't worry about this, you really don't have to know this mechanism yet. And that's still true, you don't have to know that mechanism yet. But the mechanism of formation of the chromate ester from the alcohol is a nucleophilic acyl addition. Other questions? Okay, I'm going to stop this recording and save it. Because that finishes the